Okay, in our last class, we talked about the Fermi surface, and I very briefly explain what is the importance of the Fermi surface. Because the most of case, the electron on Fermi surface are only interacting with an external perturbation, because this is the highest energy electrons, and if we have a disturbance from the outside, they start to interact with the electron at the Fermi surface. Especially many important property is related to the conductivity of the materials. So the conductivity is mainly depends on the Fermi surface. So it's very important in transport properties. And also, many magnetism is related with this Fermi surface electrons. And also, the tunneling is very sensitive on the geometry of the Fermi surface. Okay, so then I want to ask you to understand the physical meaning of the Fermi surface. So you may imagine the surface of the water in a basket. If you have a such shape and water is filling here, the surface of the water is very, very small. And if you are using water in this case, we have many surfaces. Maybe you have some experience of the wine. In a wine glass, if this is wine glass, usually people fill the wine in this height. The reason is they want to maximize the surface of the wine to interact the air to make a better taste. So it's very similar. If you make a small area, a small surface area, the interaction with the air, this liquid is very small, right? So in the real materials, the actually Fermi surface is kind of three-dimensional surface. It's so not easy to draw in the in a two-dimensional space. Usually when we take the Fermi surface in a textbook, we saw the cross section of the Fermi surface. Fermi surface is the really three-dimensional one, as you see here. The natrium looks like just sphere, and copper is it basically looks like sphere, but with small connections with the next Fermi surface. That's what you call the so there is some name of the Fermi surface based on the shape. So I'm gonna show later. And as I mentioned in the last class, all basic element Fermi surface are well studied. And let's visit this website. And if you click any materials, for example, chrome, if you are using some special glasses, you can see this one has a three-dimensional shapes. So also with the help of some software, for example, this is the let's go to the simpler. This is the shape of the copper Fermi surface, and this file extension is WRL, and this is a kind of a three-dimensional view. So you can take a look the shape of the Fermi surface in three-dimensional way. Like this. And if you search the Fermi surface, you can find such images. And also, in many textbooks, Fermi surface of copper and this. Yeah. Many textbooks, the copper Fermi surface yeah, it is. when you take a look at the Fermi space in this direction, this area looks like 노원. 개벽다리처럼 생겼죠? So the name of this Fermi space is called the Dogobon, and there are many such names. Usually the name is very funny name, but many physicists try to feel more easier to understand the Fermi level by putting the very strange names. But if you are studying this material heavily, you can easily find such name in research paper. Anyway, so let's back to this kappa again. And as you see here, the kappa shape, the Fermi level of kappa looks like sphere with some holes. Actually, this one is connection with the next Fermi surface. Anyway, so if you take a look at the other one, let's say chromium, it looks more complicated. And the different color represent the different band structure. Because one color represents SP band, the other one represents D band, and so on. Yeah, there are so many details, so I don't want to ask to students to understand too much details, but please, if you need such information, you may take a look at such a website. And also, the very Fermi surface of this one is very similar because it belongs to the same columns, and every column has very similar things. If you say, look at this one, these two guys look similar, but these guys looks quite different. But the truth is, if you fill more, a little bit more electrons, then, or if you add one more band structure, you can find the basic structure of the Fermi surface is quite similar for each columns. And from this direction, what's the change of this direction? Can increase the number of electrons. So we fill out more electrons in a band structure. So I'm going to show some example. Okay. For the chromium case, this is the band structure of chromium, and this is the band structure of the ions for one spins. And this one is the band structure of the ion band, and this guy is the chromium band. As you see here, this one looks quite similar. Only the difference is the Fermi level depends on the number of electrons. So this band diagram came from my research paper a long time ago. I made some alloy from the chromium, put some vanadium, because the vanadium is the number of electron of vanadium is smaller than chromium. So alloy means we can reduce the electrons. So the Fermi level is decreased in this way. So as you see here, the similarity of the chromium and the ion is more serious when we put the more vanadium. So as you see in this figure, if you fill more electrons or decrease the electrons, we can make a similar Fermi surface. So if you take the cross section of the Fermi surface, for example, here, this solid line, the heavy, the thick solid line represents Fermi surface of the chromium. And if you put more vanadium, this Fermi surface is getting decreased. They are shrink down, and the other one, this one is expanded. So depends on the details of the Fermi surface. For example, in this Fermi surface, this guy will shrinking down when we add on more electrons. And also this guy is expanded with the more electrons and so on. So some physical property depends on the very details of the Fermi surface. You can measure the change of that kind of properties by the alloying of the vanadium. Then we can figure out which part of the Fermi surface contribute more significantly. That's the main idea of this paper. Anyway, so the take-home message of this lecture about the Fermi level is you can alter the Fermi level by the alloy in a metallic system. It's quite different from the doping of the semiconductor systems. In a semiconductor, if you doping very small element, they make some kind of impurity band. So that's a little bit different because the doping level in a semiconductor is much, much lower. But this alloy, as you see here, we change the order of 10% of vanadium something. So we can change the Fermi level. And actually, the chrome and vanadium has a very similar band structure. So the main structure of the band is not changed a lot. Maybe it's a little bit change of band, something like this, but it's not significant. More important thing is the change of the level of Fermi energy. And the rigidness of band, you can understand this is chromium, this is iron, and it looks quite similar. Okay? Anyway, so this is the one example, the importance of the Fermi level. And in the last class, I also mentioned about the conductivity of the three-dimensional, did I say this one? 이거 지난 시간에 했던가요, 이 부분? 안 했죠? Okay, okay. Okay, so density of state, as I mentioned, the density of state is very important. And in a 3D metal, this is the alkali metals, and for example, natrium, and this is copper or silver. This is another 3D metals in vanadium, and this is ferromagnetic materials. And this cartoon is the density state. And here, if you learn the solid state physics or fundamental physics level, the conductivity of the metal system can be represented by this simple equation called the Drude model. Here, the n is the number of electrons. So if we have a more carrier, we can get a higher conductivity, sigma. And the tau is called the relaxation time. This is the average time between each collision. So means if we have a more frequent collision, then the conductivity will be small. And what is this m star? What is this m star? Yeah, that is called the effective mass of the electron at a given band. And many informational band is represented by the effective mass. Okay. Because in free electron, as we already know, the band structure usually parabolic and they proportional k square. Here k is the momentum of the electrons. And as you know, if you have a parabola, let's say this is y is ax square, then the shape of parabola is totally depends on this coefficient a. This one is large a, this one is small a, right? You can easily imagine. It's the same in band structure. The parabolic band structure you can write down in this form, and m star is corresponding the inverse of this coefficient because the other number is a physical constant. It's not changed. So depends on the m star. Actually, m star came from the curvature of this band. So such kind of band has a large m. This kind of band has a small m. And what is the meaning of large m called heavy electron? What's the large mass meaning? The meaning of mass is F is ma. It's proportional. It's proportional constant between the external force and the acceleration, right? So heavy means if we have a certain force, we got a very small acceleration. So it's hard to move. Okay, it's the same in an electron. If we have such a band, the electron is not easy to move, and such a band is the electron is more easily moved. Means it's more conductive, right? So such a band is typically S or P band, and they have a large conductivity. And this D band, this is kind of D band, which one is localized in a real space. Then they have a heavy mass, means the conductivity is small. Okay. So the main goal of this lecture about the band structure is understanding this kind of behavior. So as I mentioned, the P or S or P electron, they usually has the small beta, the large beta, the hopping integrals. So means the bandwidth is large, so they have a such kind of a parabolic shape. And for the D band, they are usually localized, so they usually very flat band. And the flat band means the density of state is high. And SP band, they have a small density of state. In other words, let's imagine the D band is localized in space, but the band structure is the K-space representation of the electron properties. So it's kind of a Fourier transform. I believe all students know the Gaussian of the Fourier transform is the Gaussian. Mathematically, it's easy to prove. And the important thing is the risk is inversely proportional for each Fourier space. If risk is small, means the sharp peak in a real space, the Fourier transform of this sharp peak in a K-space is broad. And if it's broad in a real space, the Fourier transform shows very sharp peak in a K-space. So in a D band, they are localized in a real space, so they have a such broad nature in a K band. So they have a such in a band space. This is K, and they have a such broad shape. So the density of state is usually high. So that's why the D band looks like this. And S band, usually they are very itinerant and they're moving around, means they are broad in a real space, but localized in a K space. So means they occupy very small area of K, so they show such kind of shape. Okay. So okay. So the dense state for the S band usually has such a broad shape. Actually, they have a such shape, but they fill out only this part. So all the conductivity came from the Fermi surface electrons. So number of electrons at this Fermi surface is small. But the effective mass is small, so somehow the conductivity of this alkali metal is usually good. And the normal metal, they have a D band, but the D band is deep inside of the Fermi level. They do not contribute to the conductivity. So this is the resistivity. So small resistivity means the large conductivity. And this vanadium or zirconium, as you see here, the conductivity, I mean the resistivity is much larger compared to these guys. Compared to this one, they have a order of one magnitude is larger. Why? Because the Fermi level is at the D band, and the density of state is very high, and the effective mass is very high. So the conductivity is very small. And also, ferromagnetic transition metals, we have two bands for the spin up and spin down. We have a separate band, and one band has a small conductivity, the large conductivity, and the other band has the small conductivity. And also, the reaction time is also depends on the details of the Fermi level, density of state. So you can easily understand why the resistivity of this D-band material is much larger than this noble metals. As you know, the conductivity of the noble metal, copper, silver, gold, is usually very high, right? Okay. So usually the conductivity of the this noble metal or the such kind of aluminum is usually very high because they have a acid electron filter. Okay, so that is the about the general conductivity description. But let's focus on this ferromagnetic material, which one we focused on this section. As I mentioned, even though we have a single material, but in a ferromagnetic material, we have two kinds of electrons. One is spin up and the other one is spin down. And the number of electrons, in this case, this part is more larger than the other part. So this is called the modality band or modality spin, because the number of spin in up state is more than down state. And important thing is the details of the band structure of this spin up and spin down state a little bit different. It's similar, but there's some shift. There's some shift. And especially for the D band, the S band, there's a very, very tiny small shift. So in many cases, we don't need to care about that. But for the D band, there is significant shift of the energy, and that's the source of the magnetism, actually. Because we have an unbalanced number of electrons for the spin up, spin down, we have a net spin in a material. If the number of spins for spin up, spin down are same, then they're canceled out. There's no net magnetization. Okay. And one more important thing is, based on this idea, you can easily imagine the conductivity for spin up and the conductivity for the spin down cannot be same, because all these material parameters are different, right? So it's natural. One spin is more conductive and the other spin is less conductive in the ferromagnetic materials. That's the very important feature in ferromagnetic materials. And we're going to use it for many applications. Okay, so so far I said called the D band or S band, but in a real system, there is no such distinguished band. Usually they are mixed up. So that's what you call the hybridization, right? So in a hydrogen atom, you can say this is a S band and the other one is P band. It's very clear, but it's very clear for the three-dimensional, the isolated atoms. So if we have a separate atom, means the distance between atom is very large. So we have a clear distinguished energy level. But when we shrink down the distance between two atoms, they are starting to interact, and these two energies are mixing, and they form such band structure. And as you see here, this band diagram, not just like this, but we have such kind of mixing. So this is what we call the hybridization. So in many bands has such a hybridization with different S or D or depends on the details. But for the simplicity, we can say, okay, D band, this guy has a D band crater with a small S band crater. So you can imagine what's the meaning. The D band means it's very well localized, but S band means it's itinerant. So this band has the electron belong to this band. Usually they are localized, but sometimes they can move, right? So as I talk when I talking about the MBTI, if one guy is classical E and the other one is I, E and I, okay. Nobody has 100% E. usually they have a 50% of E and maybe 30% of I, or the other way, right? So this is the same. Okay, so I hope when you taking a look some densive state of your research material, if you take a look such a shape, now you can recognize, okay, this band has a D band character with a small S band character. Okay, okay, so let's move on to the our next goal of the origin of magnetism based on the quantum mechanics. Okay, so far I give many explanation in these subsections. The main goal of this subsection is to understand this today's topic, the origin of the magnetism. When I talked about the origin of magnetism in a classical way, I said there is some interaction existing between localized moment. And I said we don't know why, but let's assume somehow there is some interaction. And today we're gonna learn what is the physical source of this interaction. Okay. Okay, so we're gonna redo classical magnetism with the quantum mechanics. Fortunately, many parts are very similar. And but as I several times mentioned, without quantum mechanics, many things of magnetism cannot be explained. For example, the QED temperature of the ferromagnetic material cannot be explained with the quantum mechanics. Okay. And I already showed this view graph several times. The spin, the nature of the spins. Okay. And this page looks quite similar. And this is the calculate magnetic moment in a paramagnetic materials with the given magnetic field. I hope this is the first homework. So you guys already take a look details of this presentation. And this is the classical version. And this is the quantum version of the similar thing. The classical way, the energy of the spins is continuous, because the all physical quantity in a classical physics is continuous value. But in a quantum mechanics, we have a discrete value. Only the discrete value is allowed. So instead of the integral is changed with the sigma, the summation is the discontinuous discrete physical quantity. And finally, we got some result. This one is a little bit different from the classical one called the Langevin function. We got a little bit more complex mathematical representation called the Brillouin functions. But if you remember the Langevin function, the behavior is quite similar. Oh, actually. The Langevin function is this one. Yeah, this is the Langevin function. This is the Brillouin function. And now we have a certain number J, which one is related to the spin momentum, the angular momentum, but just mathematical representation of Langevin function and this Brillouin function is quite similar. If you ignore this guy, and the first part is actually same. And if you take the approximation of the cotangent, hyperbolic cotangent, then we got this result for large J, the infinite J. If you take the limit of the J to the infinite, we got a classical limit, classical result. In many quantum mechanical result can be changed to the classical one by proper approximation. So there is the classical physics is nothing else but approximation of the quantum mechanics. Okay. Anyway, so the shape of the Brillouin function is a little bit different from this Langevin one. Little bit this shape, and depends on the j. The shape of the Brillouin function is depends on the j. And for the small x here, x is the ratio between the magnetic moment, magnetic energy, and the thermal energy. It's the same to the paramagnetic one. Okay, it's the same to the classical one. In the classical one, I use the s instead of x here. And for the small x means small x means this is small, so magnetic energy is smaller than the thermal energy. In that case, this Brillouin function, we can take the approximation because this guy is small, and we know the approximation of the hyperbolic cotangent, and we got this result. With this one, we can calculate the susceptibility, and this susceptibility is quite similar to the classical one. Only difference is this guy, J plus 1. Which one came from the quantum mechanics. Okay, for the large one, for the large J, large X means the temperature is small, or temperature is very low, or magnetic field is very high. Then the magnetization is exactly proportional to the J, the total angular momentum. Okay, so in a classical limit, we have such forms, and for the large J means the classical limit, and the Brillouin function is exactly same to the mathematical one. And as you see here, if you take the large J, then this guy's maybe something missing. This one should be going to this one. And also, in typical ferrite material, the J value usually half or just around the half, order of 1. So in that case, the susceptibility of susceptibility for the J is half case is a little bit different from the classical one. And this kind of paramagnetic material we call the Pauli paramagnetism for band electrons. And this kind of paramagnetism came from the band electrons, and this susceptibility looks like this. And this Pauli paramagnetism is a little bit different from the above expressions. But sometimes you can find some explanation of the Pauli paramagnetism in special materials, but usually that is not that important in many cases. Okay. Anyway, so from the understand the ferromagnetism by the quantum mechanics, as we already said, only the changing is the integral, the summations, and the Langevin function change the Brillouin functions. And I hope you guys remember this kind of a graphical solution of the finite magnetic moment. And we can obtain the so-called Curie-Weiss law, and this curve is much better than this classical one compared to the experimental data. Okay. So, as I mentioned, still there is some little deviation from this Curie-Weiss law, and such difference can be explained by so-called spin wave. Okay, spin wave is a very important concept in ferromagnetic materials because we need to understand the spin wave to understand the behavior of the magnetic moment, especially in a low temperature. Okay, so all this, okay, this is the magnetic moment, and this is temperature, and the magnetic moment is decreased when you increase the temperature, and they are reached to the zero when the temperature is reached to the critical temperature called the Curie temperature. That's the general view of the ferromagnetic material. Then why the magnetic moment is decreased? This part means all spin around the same direction. But if you turn on the temperature, there is some thermal motion involved with this spin alignment. So there is some kind of a thermal field, which one is usually random. So they start to make some random motions, and the average value is decreased. And at the Curie temperature, this randomness is now really random. So the average value of the magnetic moment is going to zero. Okay? But is it really random? That's the question. Here, even though random thermal motion uh, make some reduced energy, but every spin has a strong interaction with the neighboring spin. So making the real fluctuation and compared to the correlated thermal fluctuation, when you compare these two cases, these guys generate low energy. So they prefer this kind of thermal excitation. Means even though instead of the real random motion, they make such kind of thermal fluctuation, but still they keep the correlation between neighboring spins. So that's why we make such kind of wave. That's the not only this one is for the spins, but for the crystal lattice, when they start to vibrate by the thermal motion, instead of the real random, they make such kind of a correlated motion. This is called the phonon, and this is called the magnon. And this such kind of excitation, we can make some quantization, and you can using the such kind of fuzzy particle called the magnon, and you can explain many things. So one creation of the magnon means such kind. We create such kind of for the given magnon, they have an energy and the momentum, and is corresponding excitation of the spins of the waveform with such energy and such wave momentum. Okay, it's quite similar to the phonon. So yeah, actually, I think we don't have enough time to explain too much details of the spin waves, but please keep in mind, spin wave is a very important role in many things in the magnetism. Okay, and also if you once understand the phonon, then many parts of the physics of phonon can be applied to magnon, or vice versa. If you understand the magnon, you can apply the property of magnon to the phonon. And also not only magnon or phonon, there are many such kind of quasi particle in a solid state physics. So every solid state, such quantum quasi particle, the description of such quasi particle is very similar. Okay? So this is what you call the elementary excitation particles in solid state, and usually that requires more knowledge of the quantum mechanics for the second quantization. It's far beyond the our class course. So and also one important consequence of the spin wave is here. The temperature dependence of the magnetization is 3/2 power to the temperature, and this result well matched with this the experimental data. Okay, so without spin wave, we cannot explain the temperature dependence of magnetization precisely. Okay. Now, I would like to explain what is the physical origin of such interaction. Okay, why two spin prefer the parallel orientation in a ferromagnetic material? That's the significant fingerprint of the ferromagnetism. Ferromagnetism means spins aligned together for certain distance. Okay, So far, we assumed some called the molecular field without any reason. Just I said, okay, there is something, so believe it. Now, I'm going to explain why such interaction exists. Okay, so the answer is exchange coupling between two spins. And this exchange coupling is purely quantum mechanical. And this came from the interacting and indistinguishable electrons. What is the meaning of indistinguishable? Let's say we have a two electron, 1, 2 here. And we can describe the situation of these two electrons in a system. And then what happens if you exchange these two electrons like this? Can we distinguish them? If we have two people, they exchange, we can see there is some difference. But for the electron, we believe this fundamental particle is really identical. We cannot distinguish each electron. So we need to take care of when we change the electrons, what happens. That's what I'm saying, the indistinguishable electron nature. Okay, let's take a look. Hydrogen molecules, this is the Hamiltonian for single electrons, and the other one is second electrons. And in a previous case, we ignore the interaction terms, but we have two charged particles, so there is some Coulomb force. This is the interaction. Okay, and this one is single atom Hamiltonian. This one is same, so we already know this one. So let's say this is H0. And the total Hamiltonian with interacting two electrons is combined by the H0 with the interaction terms. Okay. And the energy of these two interacting electron is, you can write down the original, the non-interacting energy E0 plus Cij is kind of Coulomb interaction described by the potential between two particles and the wave functions. Okay. So we may play with this kind of potential well instead of the hydrogen atoms. So the physics is same. So in this case, the non-interacting electron has this energy must be just the sum of these two electrons. But if we have some interaction, the energy is changed because of this guy. So if you turn on the interactions, there's a small change of the energy by E1 plus Cij and E2 plus Cij. So compared to this one, we have a little shift of the energy for the Coulomb energy. Okay, and we have a even though non-interacting electrons, we have a two state. As we already said, learned the bonding and anti-bonding state. Okay, so due to the Pauli exclusion principle and the penalty of the fermion, what we need is we need extra term called exchange term. Means in previous page we considered the Coulomb force interaction between two electrons with the Coulomb force. But as I mentioned, what happens if you exchange these two electrons? There is some chance they can exchange each other, but we didn't know it's really happen or not. But there is some, we need to consider such interactions. So we need extra energy term called the J, which one is corresponding Coulomb force, but they change the index from 1 to 1. So this term has a certain value, is non-zero value, and there is some plus minus contribution. So the interacting energy with consideration of the spins, we have such two energy state, plus J and minus J. And because of the parity of the fermion, the total spin of the system must be something like this. For when J interaction is negative, or they can be positive, depends on the details of the string configuration. So each spin has parallel or anti-parallel. We need to care about the which case is low energy. So if the parallel spin prefer the low energy, then spin prefer the parallel state. That's what you call the exchange interaction. Okay, so depends on the two spins. This is the inner product with these two vectors. So mathematically, this exchange energy called the Heisenberg-Hamiltonian. And if the J value is positive, let's assume J is positive. And what is the lowest energy? These two spins must be parallel. If they are parallel, the inner product generate just one, right? And total system energy is lowered by amount of 2J. But compared to the antiparallel case, if they are antiparallel, then they generate -1, so the energy is 2J. So the total difference of energy between parallel and antiparallel is 4J. But this number 2, some notation people using number 2, or some people prefer the half, and depends on the book. There are many definitions, but important thing is the total energy of the system can be lowered by parallel spins amount of proportional to the J. J is the exchange energy. And look at this. These guys basically came from the Coulomb interaction, right? Between two atoms. So the distance between two atoms are very, very, very important. If they are far away, then there's no exchange coupling. Only the nearest one generate certain amount of exchange energy. So the exchange energy is very sensitive on a lattice constant of the solid state. So when you give us some stress, then the ferromagnetic momentum, which one is related to this exchange coupling energy, is changed a lot. Okay. So such kind of exchange is called the Heisenberg exchange, but there are many more kind of exchange coupling. And one of the very important one is super exchange. Super exchange existing in many oxide system. So if you are studying the oxide system, you may heard about this super exchange many times. The basic idea is here. If you have two transition metals separated by the oxygen, there's some coupling between these guys and these guys through these oxygens. And the coupling between the oxygen and the 3D metal usually occurred by the p electron of the oxygen, because oxygen has only p electron, and the shape of p electron looks like this. Okay, and this is the d electron shape of the 3D metals. So if you have a up spin here in one 3D metals, and the p electron of the oxygen must be upspin. Then, if this guy is upspin, this guy must be downspin, and this guy must be downspin. So, actually, if we ignore this electron between them, we can say there is some interaction between these two 3D metals, and this coupling is basically antiferrous coupling. And also this kind of antiphonal coupling also depends on these details of the bonding, the bonding and the distance and many things. So that's why oxide system usually such coupling is very complicated, and they show up as a very complex material properties. And depends on the temperature. There are many phase transitions in oxide materials because if the lattice constant changes, then everything can be changed. Okay? So in many oxide system, basically they form the artifact materials. But if you change this one transition metal with the other one, then it forms the ferrimagnets, and the number of phases is really high. But main idea of the super exchange is always some other atom is involved. Maybe it's not necessarily oxygen. It can be maybe nitrogen or other kind of materials. So nitride also generates making such kind of couplings. This is what we call the super exchange. And compared to the Heisenberg exchange, super exchange is a little bit longer interaction, because we need some mediation of the oxygens or other atoms. And also, one more important exchange coupling is called the RKKY interaction. Have you ever heard about RKKY? Yeah, came from the name of the four guys. I don't remember each name, but okay. This RKKYs came from the interaction, layers materials. And the layers metals and its alloy, the alloy shows various kind of magnetic properties. And in a layers material, we know they has a 4f electrons, instead of the 3d electrons for the iron or cobalt or nickel. And 4f electron is more localized, more well localized. Then direct exchange coupling between nearest layers material is too small to explain the experimental data. Here, the radius of 4f wave function is only 10% of the lattice spacing. So they are very well localized, the f electron. So people found the conduction electron mediate the interaction between these two spins. So the conduction electron, usually this is s electron, is also polarized, means they prefer the certain direction of the spins. But this polarization of the conduction electron is not very heavy. So we said that is the weakly polarized conduction electron. Then they can communicate with the F electron. So this is model called SF interaction or SD electron interactions. Anyway, so by this help of these conduction electrons, even though the F electron of each layer's material is very localized, but still they can interact with each other. Okay, but the strength of coupling strength is it should be lower than the direct Heisenberg exchange coupling. And also, this if we have some host materials, they have a F electron, and if we have assume there's some impurities, then there's some exchange coupling between them by called RKKY. Oh, here is name Ruderman, Kittel, Kashia, and Yoshida. This Kittel is the famous author of the textbook. And the important thing is, if we have an impurity, then the background charge is redistributed to neutralize the impurity charge. Means if we have a plus charge as an impurity here, we have some surrounding minus charge. And usually this minus charge is a little bit too much, so we have a next plus charge here, and so on. So we have some kind of plus minus oscillations, kind of overshoot and undershoot. So we have oscillations. This is called this is very famous oscillation in the solid state physics. I don't remember the name. Anyway, so RKKY is basically same physics of these interactions. So such kind of a change of sign, the electron polarization is same thing, same happens for the spins. So this kind of oscillation is because of the finite Fermi energy and the Fermi wavelength. Okay, maybe if I'm going too deep, it's too much. But anyway, so they should be oscillate. Oh, here is guy name the Friedel oscillations. Many physics governed by these Friedel oscillations because, as I said, many physical properties related to Fermi level. So this Friedel oscillation is depends on the shape of the Fermi surface, and that is very important. Anyway, so in a magnetic impurity, the interaction between them are oscillate but decay. So depends on the distance, the interaction sign can be changed from plus to minus. So we have many phase of the magnetic phase because it depends on this distance. In a similar material, sometimes if you change the distance, they prefer the parallel exchange coupling, means paramagnet. But if you separate more, they prefer the antiparallel coupling, so they generate antiparallel materials. So it's very, very complex phase can be used in this kind of coupling. Okay. And yeah, as I said, the sign of coupling is changed as a function of the distance. So they can form ferro or antiferro, or sometimes they form the helical structure. Helical structure means spin direction is rotating at the distance, so making some helical things. Okay. In 3D metals, Heisenberg exchange coupling is dominant, but some people said RKKY-like interaction is also important, even for the 3D metals. And also, this kind of interaction called the S interaction means the interaction between the localized electron and the conduction electron S, they interact with each other. So S electron must be polarized. So this is important to understand the spin polarized current. Okay. So sometimes the spin polarization of the conduction electron is opposite to the bulk polarization. That can be happens because the bulk polarization is depends the number of electrons, the total number of electrons. For example, like this. Okay. If this number of electrons is larger, then this is majority spins, and this will determine the spin direction. But the conduction electron is existing only this area. The polarization of conduction electron is important all at the Fermi surface. They do not care about the electron at the bottom of the Fermi level. Okay. And also, we're gonna learn about the inter-exchange coupling, inter-layer exchange coupling, which one is very important in a spin-tronic devices. And what is the inter-exchange coupling is? If you have a layered structure, for example, one ferromagnet and second ferromagnet, and there is no magnetic material between them. These two ferromagnets separated by non-magnetic material. Let's say the non-magnetic material is not that thick. Let's say a few nanometers thick. Then these two guys interact through these non-magnetic materials. The discovery of this inter-exchange coupling at the beginning is very difficult to understand because we have a non-magnetic material between them. There's no at first thought, there is no exchange coupling between them. But experimental results said there is some very strong coupling between them. So people figure out the atom in a ferromagnetic layer and the second ferromagnetic layer can interact through this non-magnetic material. And this kind of interaction depends on the thickness of this non-magnetic material. So people call this is the came from the RKKY interaction. But the truth is the origin of this interaction coupling is not exactly same to the RKKY. There's a other kind of explanation, and that is the more physically more correct. But still, people using the name RKKY to explain this one because it's more easy. Yeah, that is very important lesson. In many physical or engineering problems, at the beginning of the discovery of new phenomena, people put the name. But sometimes it turns out that it's not correct. The experimental observation is correct, but interpretation is not correct. But once you put the name, then the name is survive, even though they are incorrect name. There are many such things can be happens. So anyway, so internal exchange coupling is correct description of this kind of phenomena, but many researchers call this is RKKY coupling. But the RKKY interaction came from this nature, and this interaction coupling is similar but different phenomena. Okay, so far I said we have a atomic Heisenberg exchange coupling, and then I'm gonna explain why the ferromagnetism is occurred in a ferromagnetic materials, and let's see again based on the band structure. Okay, so as I mentioned several times, S electron is itinerant and they are more spread out, and they usually have a large beta than the electrons. Means the large beta means more easily hopping, so they can moving around more easily. And D band is localized, and usually the S band is mixed up, so we have such kind of band hybridization. And yeah, let's back to the first question. Spin ordering is reduce the entropy because they are ordering. Ordering is always reduce the entropy, but that will violate the thermodynamics. According to the thermodynamic law, entropy must increase, right? The nature like the large entropy. So why the ferromagnetism can overcome such kind of penalty? Okay, and why the spin up down band are shifted? According to the Hund's rule, electrons start to fill up the state with the parallel spins to minimize the Coulomb energy. But if we fill up the spins, the electrons with the parallel spins, there is some extra energy we need to interaction. So we can make the band shift to lower the total system energy. So actually, ferromagnetism is kind of competition between exchange energy and the kinetic energy of the electrons at the band. This is what we call the Stoner criterion. Okay, so let's go to the band structure. Here we have a spin-up, spin-down band, and the total energy of the system for the spin-up, spin-down is the center energy and plus minus exchange energy. This is corresponding the shift of the band. And the total magnetic moment is the difference between total number of spins for spin down, spin up. So we can write if you take in the density state, the integral for the density state, we get the number of electrons. So this integral gives us the number of electrons for spin up. And the next one, this guys give us n plus, and this one equal n minus. So the total magnetic moment is proportional to the difference between two density state integral. And the energy in a ferromagnetic state is this is number of electron integral, and if we multiply E, we got the average energy of the electrons. And with this extra term called Stoner exchange integral, we obtain the ferromagnetic state, the energy of the ferromagnetic state. So if the ferromagnetic state of the energy is less than the paramagnetic state, then ferromagnetic state is more energetically favorable. So the criterion is this density state at the Fermi level multiply I. Here I is the Stoner exchange integral, which is proportional to the exchange coupling energy. If they are, I skip the details of the mathematics, but if we have a large number of I multiply D, we got a chance of ferromagnetism. So to make the large number of this coupling, this physical quantity, what we need is a large density of state at the Fermi level. It should be large with a certain number of Stoner exchange integral. So large density of state is very, very important in ferromagnetism. So that's why I'm saying the density of state of the D band is usually large, and if you make a large density of state, then there is more chance we got a ferromagnetic. And also density of state and the lattice spacing is very important in a magnetism. I'm gonna show some examples. Okay, this is the ion and the band structure of ion, and for the modality and the binarity band structure of the ion. And this is the density state of the ion at this level. This is Fermi level, and this blue one and red one is details a little bit different, but overall picture is quite similar. They're just a shift of the band, right? And this is the energy difference between up and down band, right? And as you see here, if you shift one minor band, like a certain amount, let's say 2 electron volt something, then these two bands is almost identical. And by shifting this kind of band structure, we can reduce the total system energy. That's the reason of the ferromagnetism. Okay. And if we have a two band, the band difference we call the exchange energy. And this can be applied the real material. For example, this is iron, this is nickel. And as I said, the total band structure of this material is not changed. Only the Fermi level is changed. So between the iron and nickel, if you add making some alloy, what you can obtain the change of the Fermi level continuously. So more precisely in 3D metals, if we have some density state structure for the S electron, in this case, this one is the D electron. This is very schematic, but still they capture the many important physics. Depends on the number of electrons. This is the increasing of the number of electrons. The Fermi level increase because we have more electron and more electron. So we have a chance of the magnetism with a very large density of state. But if we add more electrons, we have a kappa, then no more the electron play the role. Always the electron is already occupied fully. Okay. So one more important thing is depends on the lattice parameter. If you have the lattice parameter from mangan, iron, cobalt, nickel, there's some increasement of the lattice parameter. They form the ferromagnetism, but when they reduce the moment, the distance, then we got the antiferromagnetism because of the sign of exchange coupling is changed because they very sensitive on the distance of the lattice parameter. Okay, so there is some kind of experimental data. If you increase the lattice constant of certain material, for example, mangan, if you change the lattice constant of mangan to increase something like this, then mangan turns to the ferromagnetism. Or if you reduce the ferromagnetic material lattice parameter, you can find the magnetic moment can be reduced, and so on. So lattice spacing is very important, and especially when you make the thin films, if you put some material on top of other materials, the lattice parameter is a little bit changed, and they're gonna modify the magnetic properties a lot. So for the bulk, it's not easy to making change the lattice parameter, but for the films, thin films, it's very easy to modify the lattice parameter. So we have an enhancement magnetic moment or the suppression of the magnetic moment by changing the lattice parameter. And also the density of state is also very important. Density of state is roughly say is proportional inversely to the hopping beta. And if you hopping means if the lattice is closed, hopping is increased, right? If you reduce the lattice, increase the lattice parameter, the beta is decreased. Then density of state is increased. So they are all interact each. I mean, they affect each other. Okay, this is one of the main conclusion. This is called the Slater-Pauling curve. What's the meaning of this curve is the x-axis number of electrons, and I put the atomic number here. This number is the electron number of the nickel, cobalt, and so on. And y-axis is magnetic moment. And surprisingly, this curve slope is just 1, right? This one is +1, this is -1. And all this symbol represented by experimental data. And for example, this is iron vanadium, and this is the different composition of iron vanadium. And this is alloy of the iron chrome with a different composition, but the number of electrons can be covered by changing the alloy composition. And all this kind of curve is explained by simple band model. This is what we call the Slater-Pauling curve. And for the nickel, we have a 0.6 and cobalt 1.7, iron is 2.2. And if you're mixing up, for example, iron and nickel, then we have the same number of electrons with the cobalt. And the magnetic moment is also same. Okay? So this is the, we got the plus, the minus slope in both sides. At the center is something here. And how you can explain? You can using the rigid band model. Rigid band model means we don't care about the difference band. The total band shape is maybe a little bit changed, but just keep it. And by changing the number of electrons or the position of the Fermi level, so the band shape is not changed with the alloying. It's not a good approximation, but still you can use it to explain many things. So as I already showed, the difference between the iron and nickel is the level of Fermi level, and you can explain this Slater-Pauling curve with this simple model. And very recently, in our group, published one paper called the Slater-Pauling behavior of some things. And now I hope you guys understand what I'm saying. When you're making the alloy, the Fermi level is changed, and every magnetic property can be changed. And I don't want to explain too much details, but this guy is the magnetic moment. they should follow the stratiform curve shape. And even not mass moment, but surface anisotropy and DMI energy also they are following this formula, the flatter falling curve. Then I can say this physical quantity related to the number of electrons. Okay. Okay, so this is the final view graph of today's class. I like this graph very much because to describe the band structure of the Fermi level, the ferromagnetic material, we need four energy terms. The bottom of 4s electron and bottom of 3d electrons and the Fermi level. And actually the top of band is not that important. Anyway, so this graph tells us this is a number of electrons in different atoms. And the number of, as increasing the number of electrons, the bottom of 4s electron is decreased, and all this energy is over is decreased. Means the Fermi level is increased actually. And this iron, cobalt, nickel, they are ferromagnetic material, so there is some kind of exchange coupling, so shift of the spin up, spin down state. But this graph is very low, but they tell us many information of the property of the 3D metals. It's kind of a period table for the band structure in the 3D metals. So if you have an idea of the alloying of these two 3D metals, maybe you can imagine the band structure from this simple figure. Okay, so this is the end of today's lecture and the end of the origin of the magnetism. So from next class, I'm gonna explain the next section. So about the maybe I don't remember the title, but I'm gonna change the topic. Okay. So let's finish this class. How about the homework? Is it okay? If you have any question of homework, please let me know. Okay. Thank you.